Hello everyone, welcome back to Code Staff Management. In the previous episode, we have discussed about database scaling. We learned about techniques like replication, read replicas, partitioning, sharding, caching, and database optimization as well. Right. So now in episode 8, we are going to discuss about one step deeper concept. Our topic today is distributed systems. So distributed systems are extremely important in modern applications. Like when we use applications like e-commerce platforms, banking systems, video streaming platforms, or social media applications. So there usually those things is not just one server. So there one server doesn't handle everything, right? So there may be hundreds or even thousands of servers working together. So today we will understand like what is a distributed systems, why do we need it, what happens when services fail, what are timeouts and retries, what is idempotency, what is consistency, what is cap theorem, right? So like also like what are circuit breakers, what is bulkhead patterns, what is the saga pattern, and how do we design systems that can survive the failures. So let's start from the basics. So first we will learn about the fundamental thing that what is distributed system. So a distributed system is simply a system where multiple computers or services work together to provide a single application or functionality. So let's take an example. So suppose we have an e-commerce application. So a user opens the application and searches for a product. So the request may go through like from user to the load balancer, then applicant server, then there can be like product service or in another services can be there, and those data will be fetched from the database. So there may be multiple application servers behind the load balancer. So there may also be separate services for users, products, orders, payments, inventory. So all these components work together. From the user's point of view, it looks like one application, but internally many machines and services are communicating with each other. So that is the basic idea of distributed system. Next, we will learn about like why do we need the distributed systems. So for a simple application or a small application, we absolutely can handle the whole thing with one server. But why don't we simply use one powerful server? So right? Like for a small application, we absolutely can with one powerful server. But imagine our application becomes very popular. Suppose initially we have 1000 users and one server may easily handle that traffic. But later we have suppose 10,000 users, then 1 lakh, then 1 crore. At some point, like one machine may not be enough, right? So we need multiple machines for that to handle those requests and to serve the requests. So there actually distributed systems is very much helpful because it brings the scalability, high availability, fault tolerance, large scale data processing, better performance, geographical distributions. So the important point is like distributed systems help us handle scale, but they also introduce complexity. So now the distributed systems versus single server. So let's just compare these two architectures. Like first, a single server architecture. So there we have like server and database, like client will hit the server and server will fetch the data from database. So that is very simple. So if the server has enough capacity, this architecture can work very well. But there is a problem. Like what happens if the server goes down? The entire application may become unavailable, right? So now let's look at a distributed architecture. So there the client and then load balancer, then multiple servers actually that we have discussed like in load balancer video also I have shown you like suppose the traffic will come from the users and it will go first to the load balancer then multiple servers. So now if server 1 fails, the load balancer can send the request to server 2 or server 3. So we get better availability. But now we have more complexity. So servers need to communicate with each other. Network can fail. So data needs to be synchronized and failures can happen independently, right? So this is one of the most important idea in distributed systems. Next is that thing, what is the key concept, that network is unreliable. That in a normal Java applications, when we call a method, suppose we are, suppose any banking applications or something like that, we are just calculating some price. Okay. So the method call happens inside the same process. So usually it is very fast, right? But imagine calling another service, like from order service, the request go to the payment service, and from payment service, the response will come to the order service. So now this is a network call, and networks are not perfect. So the request can take longer than expected, get lost, fail, be delayed, reach the server, but the response may get lost. So we should never assume the network call will always succeed. So this assumption creates many production problems. One of the biggest challenges in distributed systems is something called partial failure. So let's say we have three services. Suppose user service, order service, and payment service. So suppose user service is working, order service is working, but payment service is down. So the entire system has not completely failed. So only one component has failed. So this is called a partial failure. So distributed systems must be designed to handle these situations. For example, maybe we can allow the user to create an order and process payment later, or we can show a temporary error. So the important thing is that one failure should not unnecessarily bring down the entire system, right? So next, our concept is latency and timeout. So latency simply means like how much time does it take to get the response. Suppose our order service calls the payment service. So normally the response takes 100 milliseconds, but suddenly payment service takes 10 seconds. What should order service do? Like, should it wait forever? Obviously not. So that's why we use a timeout. Like, we can set payment service timeout as 2 seconds. So if the response does not arrive within these 2 seconds, we stop waiting. So timeouts are extremely important because they prevent our application from waiting indefinite time. Then we have the concept as retries. But before that, here I have only talked about, suppose, what is timeout. But I also want to mention like why timeout is important also. So just imagine like we have 1,000 requests. Okay, so if every request waits 30 seconds for a slow dependency, then our application threads can become occupied. So soon, like new requests may not get resources. So this can create a chain reaction, you can say. So one slow service can eventually affect many other services. So a good distributed system uses connection timeout, read timeout, request timeout, like that. So the exact value depends on the application. So we should not randomly choose a very large timeout. We need to consider a minimal timeout according to our business logics and other requirements. Next, that is the retries. So sometimes a failure is temporary, right? But like for example, a network packet may be lost. So the service may become temporarily busy. So in such cases, we can try the request again. So this is actually called retry. Like when one request call will be failed, then again calling the same request. Okay. So that is the retrying mechanism. So for example, like request one failed, request two succeed. So retries can improve the reliability, but there is an important warning. We should not retry everything blindly because retries themselves can also create the problem. Next, the retry storm. So imagine our payment service is temporarily unavailable. Suppose 10,000 users are trying to make payments. All 10,000 requests fail. So now every client immediately retries. So the payment service receives another 10,000 requests. It fails again. Then all clients retry again. Now we have even more traffic. This is called the retry storm. So instead of helping the system recover, our retries are actually making the problem worse. So we need controlled retries. Like the same client or same user can only retry for most of 5 times within suppose 10 to 20 minutes like that. Or for one day, if some failure will be happened, one user can retry for 10 times, not more than that, like that. Now the exponential backoff. So one common technique is exponential backoff. So instead of retrying immediately, we gradually increase the waiting time. So suppose just think at attempt one, it is failed. So suppose wait is 100 milliseconds. Attempt two again failed. Wait is 200 milliseconds. Attempt three fail. Wait 400 millisecond. Attempt four fail. So then wait for 800 milliseconds. So this gives the failed service some time to recover. We also commonly add jitter for that. So jitter means adding some randomness to the delay. But why this is important? Because suppose if 10,000 clients all retry after exactly 400 milliseconds, we can again create a traffic spike, right? So randomness spreads the retries over time, right? Next is idempotency. So now we come to one of the most important concepts, which is idempotency. So suppose a user clicks pay now. Okay. So the payment request reaches the payment service. So suppose the payment succeeds. But unfortunately, the response is lost because of a network problem. The client does not know whether the payment succeeded or not. So the client retries. Now we have a serious problem. The payment could potentially happen twice. To prevent this, we can use an idempotency key. For example, we can set idempotency key as like payment 12345, something like that. So if the same request comes again with the same key, the server knows that it is a duplicate request. So it can return the previous result instead of performing the payment again. So this is extremely important for like payments, orders, booking, ticket reservation, money transfers, like that. Okay. So I have already told about why idempotency is important. So next is consistency. So now let's discuss the consistency. So suppose we have a database with multiple replicas. We update a user's balance on the primary database, but the replica has not received the update yet. So if we read from the replica immediately, we may get the old value. So the question becomes like, how quickly should all copies of the data become consistent? So this brings us to consistency models. So two important concepts are strong consistency and eventual consistency. So first one is strong consistency. So with the strong consistency, once a successful update is committed, the subsequent reads are expected to observe the latest value according to the system's consistency guarantee. So let's take a banking example like support I transfer 10,000 from account A to account B. We don't want another operation to immediately see an incorrect balance. For critical financial operations, stronger consistency can be very important, but stronger consistency often requires more coordinations, and coordinations can increase the latency. So there is always a trade-off. Okay. Next is eventual consistency. So with eventual consistency, like different replicas may temporarily have different values, but if no new updates happen, eventually they should converge to the same value. For example, consider a social media like count. Suppose one user likes a post. It may not be necessary for every server around the world to immediately show like exactly the same count. A small delay may be acceptable. So we can use eventual consistency. This can help us build systems that are more scalable and available. So the key question is, does our business require immediate consistency? Okay. So it is not much required. Next is cap theorem. So that is one of the most famous concepts in distributed systems. So cap stands for like C for consistency, A for availability, P for partition tolerance. So cap helps us understand trade-offs when a network partition occurs. A network partition means that like different parts of the distributed system cannot reliably like communicate with each other. So during such a partition, we have to make an important choice between stronger consistency and continuous availability. So suppose just imagine there are two database nodes. Like for a like in a network, like there are two nodes, node A, node B. Okay. So now suppose the network between them breaks. So both nodes are like still running, but they cannot able to communicate. So now imagine a user updates data on node A. So what should node B do if someone asks for the same data? So if node B returns its old value, we may sacrifice the consistency. So if node B refuses the request until it can confirm the latest value, we may sacrifice availability. So this is the fundamental trade-off cap helps us reason about. Okay. So that's the network partition. Like a network partition occurs when distributed nodes cannot reliably communicate. So both sides may still be running. They may not exchange updates. Okay. The thing is like that. Next is cap practical understanding. So like without a partition, systems can provide strong consistency and availability according to their design. During a partition, the design must choose between stronger consistency and continued availability. So different systems make different trade-offs. Now, PACELC. So cap is very useful, but there is another concept which is PACELC. Like partition choose availability or consistency. Else choose latency or consistency. Okay. Availability or consistency, latency or consistency. Okay. So here PACELC, like P for partition, A for availability, C for consistency, E for else, L latency, C consistency. Like if partition, then A versus C. If no partition, then latency or consistency. Okay. So this gives us more complete way to think about distributed database trade-offs. Now we have leaders and followers. So like another common architecture is the leader and follower model. So we have one leader, the leader accepts rights, then data is replicated to followers. Okay. So we can potentially send some read request to followers. So this helps distribute read traffic. But we need to consider replication lag. Like if a follower has not received the latest update, it may return stale data, right? Now the leader selection or election. So now suppose the leader crashes. Who becomes the new leader? So this is where leader election comes into the picture. The distributed system needs a mechanism to select another healthy node. Like the new leader can then continue processing operations. So leader election is useful in systems where one node needs to coordinate work. But leader election itself is a complex distributed problem. We need to make sure that two nodes do not incorrectly believe they are the leader at the same time. Okay. Next is heartbeats and health checks. So how do we know whether another service is alive? So one common technique is a heartbeat. So a node periodically sends a signal saying I am alive. So if heartbeat stop arriving, another component may suspect that the node has failed. So we also have health checks. For example, like get slash health, we can have the endpoint like that. But remember, like a failed heartbeat does not always mean that the server is dead. Like maybe the network is down. That can be also happen, right? So this is another example of why distributed systems are difficult. Next, we have the circuit breaker pattern. So suppose order service continuously calls the payment service. So now payment service is currently down. So should order service continue sending thousands of requests? No. The circuit breaker can detect repeated failures and stop sending the request temporarily. So there are generally three states. One is closed, one is open, another is half open. So this closed means like request flow normally. Open means request fail first without calling the dependency. And half open means a small number of requests are allowed to check whether the dependency has recovered. So if it recovers, the circuit can close again. Okay. Next is bulkhead pattern. So the name comes from ships actually. Like a ship has separate compartments, right? So if one compartment gets flooded, the entire ship does not necessarily sink. So we can use the same idea in our software also. Like suppose our application communicates with the payment service, notification service, recommendation service. So we can isolate resources for each dependency. So if recommendation service becomes slow, it should not consume all our application threads. So this is the resource isolation. Next is load shedding. So sometimes the system receives more traffic than it can handle. So instead of allowing everything to fail, we can intentionally reject some lower priority requests. So this is called the load shedding. For example, during extreme traffic, we may prioritize payment, order creation, and login, and temporarily reduce the recommendation, analytics, non-critical notifications. So the goal is simple, like protect the most important functionality, like payment, order creations, logins. Those are important. So we will only keep as active, but others we can stop. Next is back pressure. So back pressure is another important concept. Imagine a producer generates 10,000 messages per second, but the consumer can process only like 2,000 messages per second. So what happened? The queue keeps growing. Eventually, memory or storage can become a problem. So back pressure allows the system to control the producer when the consumer cannot keep up. So this helps prevent uncontrolled resource consumption. Okay. Next is rate limiting. So rate limiting controls how many requests a client can make, like 100 requests per minute per user. So if the user exceeds the limit, we can reject or delay additional requests. So rate limiting helps protect against abuse, accidental traffic spikes, DDoS like application traffic, expensive API usage. So we have some common algorithms also for that, like token bucket, leaky bucket, fixed window, sliding window. Okay, we will discuss those things later as well. Next is distributed locks. So sometimes Multiple servers need to access the same shared resource. Suppose two servers try to process the same job simultaneously. So we may need a distributed lock. The basic idea is like server A acquires a lock, server B will wait. Server A completes the work, then server A release the lock, and then server B will proceed. So that's the idea. So like, but distributed locks are not simple. We need to consider the lock expiration, server crashes, network failures, lock ownership, duplicate executions. These concepts we also need to consider. So we should use distributed locks only when really necessary. Next is distributed transactions. So now imagine an order requires multiple operations like create order, make payment, reserve inventory, create shipment. So these operations may belong to different services. How do we make sure everything succeeds together? So this is the distributed transaction problem. So a traditional database transaction is easier because everything may happen inside one database. But across multiple services, network failures can occur between steps. That's why distributed transactions are much more complicated. After that, saga pattern. So one common solution is saga pattern. So instead of one huge distributed transaction, we divide the workflow into smaller local transactions. For example, like order to payment, payment to inventory, inventory to shipment. So each service performs its own local transaction. But what if inventory fails after payment succeeds? So we may need a compensating action. For example, like refund the payment. So this is called the compensating transactions, right? So Saga is very useful for long running business workflows. Okay. Next is message queues. So message queues allow the services to communicate asynchronously. So they are, suppose order service is there, then with some queue, like it will, the communication will happen to the notification service. So order service does not have to wait for notification service to finish. So it can put a message into the queue. The notification service can process it later. Okay. So order service does not have to wait for notification service to finish. That is one example I'm just giving. So like the order service can put some message into the queue and the notification service can process it later. That's like usage of message queues actually. So this provides decoupling, traffic buffering, asynchronous processing, better scalability. Okay. Next is at least once delivery. So now comes in like an important message delivery concept, like how the message delivery system will work, like at least one delivery. So it means the system guarantees that the message will be delivered at like at least once. But there is a possibility that it may be delivered more than once. Like messages will go to consumer, processing can be successful. So, but after that, just think if suppose acknowledgement lost. So then again, message will go to the consumer. So the consumer needs to be prepared for duplicates. So this is why idempotent consumers are very important. So that's why it means the system guarantees that the messages will be delivered at least once, right? Now, exactly once. So just see, at least once and exactly once. These two are different. So we often hear the term exactly once, but exactly once processing is difficult in distributed systems. Why? Because there can always be a failure between two operations. For example, like consumer processes messages, consumer completes the database update, consumer crashes before acknowledging the message. So the message may be delivered again, So in real world systems, we often use idempotency, deduplication, unique constraints, transactional processing, retry mechanisms, instead of simply assuming that a message will execute exactly once. Next is message ordering. So another problem is ordering. Like suppose we have three events like create account, add money, withdraw money. So if they are processed in the wrong order, we can get incorrect results. So we need to ask, does ordering matter for the system? If ordering matters, we need an appropriate design. But global ordering can reduce scalability. Many distributed systems guarantee ordering only within a specific partition or stream. Next is time and clocks. So another surprising problem is time. We may think all servers have the same clock, but they don't. Different machines can have slightly different times. This is called the clock drift. For example, in server A, the timing is 10:00:01. Server B, timing is 10:00:03. So if we use timestamps blindly to decide which event happened first, we can make mistakes. For distributed ordering, systems may use sequence numbers, versions, logical clocks, event ordering mechanisms. Okay, we need to use those things. Next part is the observability. Like distributed systems require a strong observability. Why? Because one request can travel through many services. For example, like from client through the API gateway, the request goes to the order service, then to payment service, then database. So if the request fails, where exactly did the problem happen? We need three important observability concepts. One is logs, like tell us what happened. Another is like metrics, which tells us how the system is behaving. Then traces tells us how one request traveled across the services. Okay. So a trace ID can help us connect the logs from multiple services belonging to the same request. But these combinations of these logs, matrices, metrics, traces, okay, logs, metrics, traces, with the help of these things, we can get a proper idea. We can observe the request flow. Okay. Next is failure handling strategy. So when designing a distributed system, we should assume failures will happen. We should think about timeouts. Don't wait for forever. Okay. We have to think about retries. Retry temporary failures carefully. Also, we need to think about backoff. Like don't retry continuously. Next, idempotency. Make the repeated requests safe. Next is circuit breaker. Like stop calling an unhealthy dependency. Bulkhead is we need to isolate the resources. Then we need to consider the rate limiting for controlling traffic, load shedding to protect critical functionality, monitoring to detect problems quickly. So this is what makes a system more resilient. Common mistakes, what we do. So infinite retries. So never retry forever. Mistake 2 is no timeout. So a request should not wait indefinitely. Mistake 3, retrying payments without idempotency. This can potentially create duplicate payments. Mistake 4 is assuming the network is reliable. Network calls can fail. Mistake 5 is ignoring duplicate messages. So at least once delivery can produce duplicates. Mistake 6, no monitoring. Like if you cannot observe the system, debugging becomes very difficult. Mistake 7 is over engineering. Like don't introduce Kafka, distributed locks, or complex coordination mechanisms without a real requirement. So always start with the problem, then step by step narrow down and then make the solution. Then with a real world example, like how the ordering system works, we can know. Like suppose a user places an order. So the request reaches the order service. The order service communicate with payment service, inventory service, shipping service. So we can use synchronous calls where an immediate response is required. For background task, we can use a message queue. For example, like here from users or client to order service. Then order service communicate with payment and inventory service. We can make like we can use one queue which will do the notifications and analytics as well. So now we can add the timeouts, retries, idempotency, circuit breakers, rate limiting, monitoring, distributed tracings. So this gives us a like much more resilient architecture. Now, how will be your system interview approach for distributed systems? So if you are preparing for a system design interview, don't just draw boxes. You should also explain like what happens when something fails. For every important service to service communication, you always ask what happens if the service is slow? What happens if it is unavailable? What we should do? Like we need to implement retry or not? How many times? Should we use exponential backoff? Is the operation idempotent? Do we need strong consistency? Can we use asynchronous processing? Do we need a circuit breaker really? How will we monitor the failure? So this approach makes your system design answer much stronger. Next, summary of this episode 8. So let's create a simple mental model. So when designing a distributed system, first understand the requirements. Second, you need to identify the services and data flow. Third, you need to identify where network is, how the communication happens. Fourth, for every network call, think about timeout, retry, backoff, idempotency. Fifth, you need to think about consistency. You need to ask like, do we need strong consistency or is eventual consistency acceptable? You also need to think about failure isolation. You need to use like circuit breaker, bulkhead, rate limiting, load shedding. You also need to think about asynchronous processing. You can use message queue, consumer, retry, dead letter queue, DL queue. And finally, you need to monitor everything. Okay. So a distributed system contains like multiple machines or services actually which work together. So distributed systems help us achieving like scalability, availability, fault tolerance, performance, but they also introduce new challenges like networks can fail, services can become slow, messages can be duplicated, data can become temporarily inconsistent. Therefore, we need proper failure handling strategies. So you need to remember these concepts. Okay, like retries, backoff, idempotency, consistency, cap theorem, circuit breaker, bulkhead, back pressure, rate limiting, saga, observability, all we have discussed. So before we finish, there are some important interview questions you should practice what we have discussed already. Like what is distributed system? Why do we need distributed systems? What is a partial failure? Like why are network calls different from local method calls? What is a timeout? How should retries be implemented? What is exponential backoff? What is real storm? What is idempotency and why is it important? What is strong consistency? What is eventual consistency? What is cap theorem? What is a network partition? What is PACELC? What is a circuit breaker? What is a bulkhead pattern? What is back pressure, rate limiting, distributed lock? What is distributed transaction? What is the saga pattern? Why are message queues useful? What is at least once delivery? How do you handle duplicate messages? How do you design failure handling in microservices? So these questions are important for this episode. So that brings us to the end of the system design episode 8, distributed systems fundamentals. So in this episode, we learned not just how distributed system work, but also how to think about failures, consistency, communication, and reliability. So these concepts are the foundation for many advanced system design topics. So in the next episode, we will move towards API gateway, load balancing, and traffic management, where we will understand how incoming traffic is controlled and distributed across our services. So if you found this episode useful, subscribe to Code Management and continue with the system design series. Thank you for the watching. So see you in the next episode.